Hi, everybody. So we're going to continue our discussion of sequences of numbers, not necessarily geometric and arithmetic that we talked about before, but any sequence of numbers. We're going to be given some explicit formulas to get to the nth term in certain sequences. And what we're interested in is, where do these sequences go? Remember, these are infinitely long lists of numbers. And I'm kind of curious to see, where are they going as the number of terms approaches infinity. So again, you need to make sure you got your notebook here. No formulas really here today. Well, there's one thing that we might want to make sure that we jot down, and that could be on a foldable or your note card. So let's hop in and take a look. In fact, pretty easy kind of topic here. So here are three examples of explicit forms, formulas for certain sequences. And in fact, if you want to pause for a second, go ahead and pause me, and then maybe try to write out the first couple terms in each of those sequences. Again, we pick n values of 1, 2, 3, pick n values of integers starting with n equals 1, and just write the first couple terms and see what you get. All right, so we can take a look at these two different ways. We can kind of look at them numerically, and then I want to also take a look at them graphically. So when I look at this first sequence, as I put in things like 1, 2, 3, so that's 1, a half, a third, a fourth, a fifth. What seems to be happening there? Well, they seem to be getting smaller and smaller and heading towards 0. Now, will we ever reach 0? Not necessarily, because there's an infinite number of numbers here, but ultimately I'm going to be approaching 1 divided by infinity, which is extremely, extremely small. What about the next one? So this series converges, we say, and it converges to a value of 0. The nth term converges to 0. What about this next one? I start putting numbers in. Well, if I put in 1, I get negative 1 times 0, that's 0. How about 2? So that's going to be positive because of the even exponent times 1. And then I'm going to get negative 2, then positive 3, and then negative 4. It's kind of going back and forth, but getting bigger and bigger. That's interesting. I don't know if that's heading towards something or not. Is that converging, or what do we say, diverging? I think it's getting bigger, but it's also flip-flopping back and forth, positives and negatives. What about this last one? Well, I also see this negative 1 to the nth. That means it's going to flip-flop back and forth, positive, negative, positive, negative. But where eventually are these numbers going to head off towards as n approaches infinity? Well, this expression, I hope you can see, is maybe going to be heading towards a value of 1. You can almost see that there's a horizontal asymptote there from what we had looked at in the past, back in pre-calculus. Well, let's take a look at, hi there. Let's take a look at this graphically. So here's this first example, 1 over n. And what I'm going to do is I'm going to graph this. I'm in Desmos. I've got it set up to just graph the integer values. So as I let n increase, it's going to then plot the points. So a half, a third, a fourth, a fifth, sixth. Actually, it's going in between some of these as well. So you can see they're getting smaller and smaller and smaller. And you can even see now I've got 24 elements in this list. And it's heading towards 0. So we were right. That first one, 1 over n, or 1 over, in this case, I'm typing it in 1 over x, heads towards 0. That converges to 0. Now, does it actually reach 0? No, it's never going to reach 0. So I've got this reciprocal function. But at least we can say it seems to be converging towards a value of 0. All right, what about the next one? So I see that plus minus term here, the negative 1 to the nth, which will go back and forth. And those terms, as n increases, those values, I'm just, again, remember that these x's are n's. So I'm getting this ping-ponging back and forth, positive, negative, positive, negative, positive, negative. But as n, or in this case x, increases, the values increase. So this is definitely diverging. It's going off in 2 different directions. So does that mean that all alternating, we call this an alternating sequence because it goes positive, negative, positive. Do all alternating sequences diverge like this does? Let's look at this next one. So this is my next one with going back and forth. And then, so this is going to be going positive, negative, positive, negative, positive, negative. But pretty quickly, only after 34 terms in this element, it's getting pretty close to 1. But it's going close to 1 and then also -1. So this is also diverging because it's approaching the opposite number on either side, but it still is not approaching one particular number. So what do you think? Do you think it's possible to converge if it's alternating? I hope you're saying yes, because if I think of something like exponential coming in underneath and above, maybe we could from both sides approach 0. So we can look at these graphically, and you could do those on your graphing calculator and kind of see what's going on with these graphs. There is a way to change your calculator to sequential mode to deal with sequences, but I think they're just easier or necessarily from the graph. All right, so let's hop back into here. We took a look at those. And now let's take a look that there is a more systematic approach. Instead of thinking about it numerically or looking at it graphically, because we might not always have our calculator, we can look at it algebraically. So how about this sequence? Does this sequence converge? So really what's happening is we're looking to see what happens is these sequences approach infinity, or as n approaches infinity. And hopefully at this point you would have said, Mr. Godek, aren't we just talking about limits? And the answer is yeah, we're talking about limits. So if we can check what the limit as the nth term approaches infinity, we can see if it converges. And not only that, but we can see what it converges to. So what is the limit as n approaches infinity of this? Do you know by just looking at it? Well, hopefully you can see that you would get infinity divided by infinity, which means it's L'Hopital. In fact, 1 L'Hopital away would give you a limit of, as n approaches infinity, of 2 over 1 after you differentiate. So it seems like it's going to be 2. Plus, I can also see that this function, from my pre-calc background, this function has a horizontal asymptote if I use my n behavior model. So it seems to be approaching 2. So let's look at it. If we didn't know L'Hopital's rule, I could then maybe separate the fraction with its common denominators, and then I could separate the limits. And that first limit, well, the n's are going to cancel out. So what is the limit as n approaches infinity of 2? Well, it's a constant function. It just stays 2 the whole time. So this first limit is just going to be 2. What about the second limit? Limit as n approaches infinity of 1 over n? Well, that's the first one that we did. So as the denominator gets really, really big, the fraction is going to get really, really small. So I get 2 minus 0, which as predicted was 2. So the sequence does converge, and it actually converges to a value of 2. So the first 5 terms in there, if I actually put them in, n equals 1, 2, 3, 4, 5, this is the numbers I get. So 1, 1.5, 5/3, 7/4, 9/5. Hopefully you can see that as we continue, the numerator gets closer and closer to being twice the denominator. And I'm going to go back in and hi there. And I'm going to check one more graph here. And where's my last one? Here we go. That's this one. And as I increase n, we can see very quickly it gets really, really close to 2. It's never going to hit 2, but it's going to get pretty darn close to 2 as we increase n. So graphically, we can show that as well. All right. Here. All right, how about this one? Does this sequence converge? This is a fun one. All right, maybe kind of playing around with this one, thinking about the limits. All right, well, in this case, this cosine function, that's a little bit different, but the cosine function, I don't know, does that really grow or get really, really, really big, or does it get really, really, really small? No, it kind of bounces back and forth between 1 and -1. So that particular term just goes between 1 and -1. So therefore the numerator is staying between the numbers 1 and 3. So that numerator is not getting very big. It's not getting very small. It's just bouncing between values between 1 and 3. But what is the denominator doing? Well, good grief, that denominator is going to get really big. Well, let's take a look at a method that we can solve this, knowing that the numerator is going to stay somewhere between 1 and 3. So I can sandwich this limit in between two other limits. So my numerator is going to be as big as 3, so I can say equal to here, and it's going to be as small as 1, and set equal to here. Well, what are these limits on the ends? As n approaches infinity, 1 over n, 1 divided by infinity, well, that's going to get close to 0, square root of 0 is 0. Same thing over here, 3 divided by infinity, that's going to get really, really big denominator, really, really small fraction heading towards 0, and the square root of 0 is 0. So the limits on the ends are both 0. And if this function is sandwiched in between these two other functions, then I know that it's going to, my given function is going to converge to 0. So by the sandwich or the squeeze theorem. So there's an example of how we could do that too. Now, if that was the case, I don't know if I would always go to that method, because again, the numerator is just going back and forth between values between 1 and -1. The denominator is getting really big without bound. It's just growing and growing and growing. So therefore, this fraction is going to get really, 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 really small and head towards 0. And the square root of 0 is 0. All right. So here's what the sandwich, or we sometimes call the pinching theorem. If I've got a function that's sandwiched in between two other functions, so here's some dotted points just like I did earlier. So I've got a sequence, I shouldn't say function, sequence of numbers C that's above here, and a sequence of numbers here, the open circles A down below, and B is a sequence that is in between those other function or those sequential values. Then the limits, have to be sandwiched as well. All right. Another thing we'll keep in mind is the absolute value theorem for sequences. If the absolute values of all the terms, remember those terms that ping pong back and forth, going positive, negative, positive, negative. If the absolute value of those terms converge to 0, then the entire sequence converges to 0. Think about it. You would take all of those negative values and reflect them above the x-axis. So if all of those terms headed towards 0, then the sequence heads towards 0 or converges towards 0. All right, how about one last one here? One that's really kind of wacky. So again, we could think about, well, the numerator, let me get my limit in here. My numerator is going to grow. It's going to go to infinity. And my denominator, well, e to the infinity divided by 10, well, that's exponential. That's also going to head towards infinity. So they both head towards infinity. It's not like the denominator only is heading towards infinity like the other ones. So what can I do here? Oh, I've got a limit that's infinity over infinity. Sure, I can use L'Hopital's. So let's use L'Hopital this time. So my new limit, after I take the derivative, don't forget to include the limit notation. So I take my derivative of the numerator, derivative of the denominator, little chain rule action going on there of 1/10 or 0.1. But I check this, well, that quadratic's still heading to infinity. That exponential's still heading to infinity. It's just now multiplied by 1/10. So still L'Hopital again. So let's go again, derivative of the numerator. Derivative of the denominator generates another 1/10. So now I got 1/100th down in the denominator there. Check. I think it's still heading towards infinity in the numerator and the denominator, but I think I only got one more to go. I'm at a linear term up in the numerator. One more derivative gets rid of that n. Now I get 6. The denominator is still heading towards infinity. Now it's not heading there as quickly because of that 1/1000th now there, but it is heading towards infinity. So that very large denominator is going to create a very small fraction and have a value of 0. So this sequence then turns to 0. All right, so in the end here, we can see whether or not sequences converge or diverge simply by taking the limit as n approaches infinity. And this is a fantastic use a lot of times of the use of L'Hopital's rule and the pinching and the squeezing theorem. So time to do a little bit of practicing. All right, good luck.